I am deeply honored by being selected as a 2014 recipient of the Jun-ichiroTanaka Distinguished Achievement Award from the International Precious Metal Institute. To receive this recognition from such a prominent organization is particularly gratifying. Indeed, it is quite challenging to prepare remarks that can be meaningful to such a distinguished audience having quite diverse interests. Thus, I thought I would talk about an aspect of a person's career in science by addressing the question of what led me to pursue studies in the exploration of precious metals to address problems of how to facilitate the design of structure for function, regardless of the structure complexity, to solve problems that are important for the well-being of society. Many discoveries in organic chemistry historically have their origin from natural products. Indeed, my interest in palladium did stem from a project for which I was personally doing the experimental work during my time as a junior faculty member at the University of Wisconsin, the identification of a natural product called juvenile hormone. At the time, there was the beginning of a thrust towards replacement of toxic synthetic pesticides with more environmentally benign agents. The maturation of insects involves a series of molts, from larvae to pupae to adults, that are believed to be controlled by 3 hormones. One of these hormones, ecdysone, initiates the molt. A second hormone, the juvenile hormone, prevents the molt. It was hypothesized that juvenile hormone could lead to new types of pesticides. In 1966, 2 of my colleagues at the University of Wisconsin, Herbert Roller and Carl Dahm, were isolating this compound. We were then challenged with determining its structure, a critical first step. We eventually did determine the correct structure, which appeared to derive by converting commonly available natural products wherein a 1-carbon subunit was homologated to a 2-carbon subunit. Pondering this discovery, I wondered if there could be a synthetic process that would allow us to perform synthetically such a homologation process. This chemistry led us to broadly examine the process we termed allylic alkylation, utilizing palladium. Our work began in the late 1960s, prior to the discovery of metal, notably palladium catalyzed cross-coupling, and shortly after the palladium catalyzed olefin arylation, both of which shared the Nobel Prize in 2010. Indeed, our venture into palladium catalyzed allyl alkylation stimulated the development of the broad class of metal catalyzed allylic alkylations. We and others have shown that variation of the choice of the metal provides complements in selectivity, making this tool in our synthetic toolbox an ever more powerful one in facilitating complex molecule synthesis. What we have developed helps improve synthetic efficiency, which in turn greatly facilitates the discovery and development of new substances that are core to function. While academia typically equates efficiency with selectivity issues, it ignores an equally important component of efficiency: how much of what you put in your flask ends up as your product. For simplicity, I refer to this component of efficiency as atom economy. An ideal synthetic chemical reaction is one wherein 100% of the reactants end up in the product, with anything else only being needed catalytically. Indeed, historically, selectivity issues trumped atom economy. The ability to use transition metals to activate CH bonds chemoselectively led us to ask specifically if we could solve selectivity problems but simultaneously maximize atom economy. One of our first successes was our evolution of a version of palladium catalyzed a little calculation into a simple addition. This mission led us to another precious metal, ruthenium. By semi-rational design, we have created a treasure trove of more than 30 atom economic additions and are counting. Many people have the notion that because we can do so much more than we could have ever done before, we have all the tools we need in our synthetic toolbox. However, nothing could be further from the truth. There is a trite saying, you don't know what you don't know. In our ruthenium catalyzed studies, using just one ruthenium complex, we have already developed over 30 atom economic addition reactions. Considering how many different ligands and how many different types of precious metal catalysts that can function as catalysts, how many reactions can we really conceive? The number of possibilities, without question, is astronomical. The only limitation of how many new synthetic tools are possible is one's imagination. Undoubtedly, we have barely scratched the surface of what can become possible. The precious metals, notably palladium, have led us into this new world and has had an immense impact on how chemistry can be practiced to better achieve function through structure in so many ways that have impacted society's well-being. It is perhaps why palladium has been referred to as the metal of the 21st century. I feel fortunate that I have been able to help lead the way. It is especially gratifying to see one's efforts being more broadly appreciated by my selection as this year's recipient of the IPMI Tanaka Distinguished Achievement Award. I truly regret that I am not able to be with you in Orlando on the occasion of the IPMI annual meeting. I hope the event will be a great success. Thank you so very much.